John Charles from GSC, Chief Scientist for the Human Health Program. Dr. Dave Beatty from JPL, he's the Mars scientist. And then Ben Donahue at Boeing Company. We'll be talking some of the transportation options. So we have charts, which we do. Why don't I get going? So what I wanted to do, what we wanted to accomplish in panel one is set the stage for the conference. Try to give you a feel for some of the challenges associated with human exploration of Mars. Because of the breadth of topics, we won't be able to go into all of them, so we've chosen some areas that are some of the key challenges, and we'd be more than happy to talk to you about some of the areas and some of the breaks or over lunch. So what I will do is go through the current NASA design reference architecture and use that to help frame some of the discussions for human exploration of Mars. We, within the agency, have been keeping up a design reference architecture to serve as a benchmark of how we might explore Mars. It is not necessarily the way in which we will explore the planet. We use it to compare and contrast different ideas, new approaches, so that we have a common reference to assess different technologies and system concepts. So we're constantly updating it as we go along. We have the latest version is what we call Design Reference Architecture 5.0. It was a body of work that was finished in the 2007 time frame, and it was published in 2009, formally documented in 2009. We're currently starting the next process of updating that. So we'll go through another approach to compare and contrast different approaches. And when that body of work is done, we will update the design reference architecture. So again, it's used to help frame some of the discussions, used as kind of just a common reference to compare and contrast different approaches. In order to help frame some of the discussions, you need to understand human round-trip missions are a little bit to Mars are a little bit different than what we typically think of for space station or what we had with Apollo. In those missions, the Earth was the central body. The Moon, space station, orbit Earth. And so, from a broad perspective, you can come and go to and from those destinations almost any time within certain constraints, almost any time you want to. So if the problem arises, you have the opportunity to come home. For Mars missions, the Sun is the central body. Both Earth and Mars are orbiting the Sun. And so it's important to understand, and you design the mission, you have to plan the mission, not only the outbound trip to rendezvous with the planet, but you have to keep in mind where Earth will be on the return trip. And the relative phasing of Earth and Mars and the trajectories force you into two general classes of trajectories. Over on the right, you see what we commonly refer to as the short stay type of mission approach. That's sometimes called an opposition type class mission. And you can see the mission profile in that is generally characterized by one long transit out to the planet and one short transit. We generally try to shape the mission so we have a short transit out to Mars so that the crew is less deconditioned, get those transits down to about 180 days or so. But when they get to Mars and this fast transit out, Earth is in the wrong location to come home, and every day you stay on the planet, it gets worse. So there's a general tendency to try to get to the surface, explore as quickly as you can, and then start that transit back. And generally the transit back involves a Venus swing bite. Pick up a Venus swing bite to help you with the trajectory, to help reduce the velocity requirements. The other approach shown on the left, or second, sorry, on the right, is what we call the long stay mission, or commonly referred to as a conjunction class mission. In that mission, you dash out to Mars, and when you get there, instead of staying a short time and then chasing Earth back, you decide to stay for a long period of time. Stay up to about 500 days exploring the planet, waiting for that proper alignment of Earth and Mars so that you can dash back home again. So generally, the velocity requirements, which is very important to us from a mission planning perspective, because that drives the launch vehicles, drives the propulsion systems, is very important to understand and try to minimize those as much as you can. And with the left-hand side short stay type mission, there's a large variation in the amount of energy required to conduct that mission. Whereas the conjunction class mission are fairly stable, and they're the less required in terms of transportation section. But from a human health and risk perspective, it's also important when you understand those mission classes to understand the total trip time associated with them. And you can see over there on the left, the opposition class, which is the short stay mission. You can see the bars associated with the outbound trip, the time that you spend there, and the return trip. The mission durations are on the order of about 18 to 22 months, total mission duration. And you're only spending 30, 60 days at the planet. So most of your time is spent in free space, the radiation environment, which Return Golden just talked about, zero-G gravity environment, traveling out to the planet and back, and only 5% or so of your time is spent at the planet in a gravity environment. Conversely, the long stay mission, you dash out to the planet, but you spend about 500 days on the surface, and then dash back in about another 180 days. So each one of those transit legs on the long stay mission is essentially what we demonstrate every time we send a crew to space station. Crew rotation to space station is 180 days. Each one of those transit legs on the long stay is equal to that. So it's very important from a human health perspective, from a total system reliability perspective, and maintenance of systems. The mission durations are important. And you see that they're, from a general perspective, they're the same. Long missions, regardless of those mission approach you have, they're still long missions. They're on the order of 18 to 30 months long. So those can serve some significant challenges in terms of the overall exploration strategy for Mars. But then you say, well, you look back at history, we've done this in the past. I mean, human explorers exploring the new frontiers have conducted missions like this in the past. It's not necessarily new to the human race. It's just a matter of, do we have the will and the wherefore to actually conduct those types of missions. So we know we can do it. We have historical precedents. It's just a matter of getting on with it and actually doing it, hopefully. This is the design reference architecture. I want to use this to kind of walk you through the mission sequence. And we begin it with what we call a split sprint approach. We pre-deploy cargo to the surface of Mars ahead of the crew in order to help reduce the risk and also enable some other architectural strategies. So we see here some heavy lift launches of vehicles to low Earth orbit, use automated rendezvous and docking of the systems in Earth orbit, trying to minimize the complexity of assembly. Get those vehicles checked out in Earth orbit and then send them on low energy transfers to Mars. Take about a year to get to Mars. And when they get to Mars, we use aero capture using the atmosphere of Mars to slow down and capture into Mars orbit. We land one of the vehicles to the surface of Mars. And that is actually the ascent vehicle. We produce propellants from the atmosphere of Mars. Extract the oxygen, produce oxygen for ascent. Also produce some of the life support equipment, life support consumables. So that allows us to not only reduce the mass, but also some of the size of the vehicles. And we do that before we send the crew. So we know that propellant is there and it's produced before the crew ever leaves Earth orbit. About 26 months later, we then launch the crew elements, launch those in low Earth orbit, again rendezvous and docking to get them checked out, and then transfer the crew to Earth orbit and then out to Mars, again at one of these fast transits to Mars. We chose in order to reduce the total energy requirements, plus in order to maximize the exploration capability, this long stay approach, staying at the planet for about 500 days. Once they get to Mars, they rendezvous with their habitat lander. They're going to be deconditioned. They've been traveling through space for about 6 months. We'll do our best to get them conditioned as best we can when they get to the surface, but they will be deconditioned, so we land them in the habitat lander. Also for Mars entry and descent and landing, you're flying through an atmosphere. You don't have abort capabilities like we